So cool guys, today we'll be discussing the Codeforces round 862 that was rated for Dev 2. We'll be solving the first four problems, or we'll be discussing the first four problems. The problem A is we need the zero. The problem states that you are given a array A consisting of non-negative integers. Now we can choose an integer x and denote another array B, the ith element of which is equal to ai XOR x. So all of the elements of B would be dependent on the corresponding elements of A, and the thing would be that bi would be equal to ai XOR x. And the thing that should hold is that after for all these elements of array B, if we take a XOR, that should equal 0. So how can we do this? This is a very straightforward and easy question. Shouldn't take more than 2-3 minutes if you have the basic understanding of XORs and of basic mathematics. So what you can do is you can say that if the number of elements over here, if they're even, okay, let me just go over here. Cool. So let's say the number of elements in the array A, if they already have a XOR that is equal to 0. If their XOR is already equal to 0, then I can say the value of x is 0, right? So my B would become exactly equal to A, and still its XOR is gonna be 0, right? So that is one case. So let's discuss the number of cases that we can have over here. Okay, give me a second. Sure. Cool. So one case is that the XOR. So let's denote this as XOR. There's no symbol for XOR, but this is XOR. So XOR of A is 0, then the answer definitely exists, and our answer is x is equal to 0. Now the other case is that there's an array A which has some element. Let's call it XYZ, or XYZ is also used. Let's call it DEFG, right? Now for these elements, the XOR is some non-negative number or some non-zero number. Let's call this number as y, right? Now what you can say is that the number y needs to be added. So its XOR value is y. Now this is the array A, this is the array B I'm making. So I'll say the array B would be y XORed with the current element. So this would be y XOR D, this would be E XOR D, this would be F XOR, y XOR D, y XOR E, F XOR E, and then G XOR y. Whatever the values are, just XOR them with y and write down the values. Now what would happen in this case is that after you have all the elements written, so there can be two cases. The number of elements you were having, then they can be even or they can be odd. Now if your n or the number of elements are even, in that case there would be even occurrences of y also. So y would occur even number of times. Even number of times. As soon as y occurs even numbers of times, it would when we are XORing it up, it would become 0 automatically, right? So in this case, the XOR of array B would still be the number y itself, right? Because we know that D XOR E XOR D XOR E XOR F XOR G was already y. Since the number we actually XORed it with, the additional number we added, is itself becoming 0. So this equation will still hold, right? The only condition where this equation would not hold is that when n is odd. So when n is odd, you will be XORing y odd number of times. So even number of y's would cancel out themselves. So a single occurrence of y would remain. In that case, your final answer would become 0. Cool. So that is what we had to check. So what we did is that we took the three numbers. Okay, over here. Okay, we took the number n, we took the vector v. Then firstly I checked the entire XOR. If the XOR is already 0, I have the answer 0. If the XOR is odd, in that case the answer is x, or the answer is the XOR I already calculated for this number, else the answer does not exist. So there are these three conditions only that you need to check for this question. So a very basic question. Let's move to the next one. Any doubts in this? Okay, cool. So the next problem is the string has a target. So the problem states that you are given a string S. You can apply this operation to the string exactly once. Choose index I, move the character Si to the beginning of the string, remove its old position. For example, if you operate with this index I equal to 4 in this particular string, so index I equal to 4 is this one, right? So you'll move A to the front of it, and this A won't be present over here then, right? That's obvious. So this would become AA, B, A, C, D. So we can do this operation exactly once. Bro, someone's... Okay. So we can do this operation exactly once. So after doing this, we want to construct the lexicographically minimal string. So how would we do that? So because we want to do it greedily, or we can do it greedily, so we'll choose the minimum index or the minimum value that is present in the string, and we or the minimum character that is present in the string, and we'll bring it to the front. And it's also the case that we can only do it once. The only case or the edge case over here is that what if a number or a character is present multiple number of time. So let's discuss that particular case. So let's say my string, I have a string that is ba. Now it's very obvious that the best answer you'll get is by picking a and moving it to the front. But which a would you like to pick? Would you pick this particular a, this one, or this one? That's the question. Now you can also decide this greedily, because if you pick the last one, right? So if you pick the last very a, then the front actually remains the same, because in the front you are having a itself, but the remaining string is also lexicographically smallest, because the minimal elements that were present to the left of it were not shifted or were not disturbed, right? So the left of the string, which had a more significant value, still has the same value. You did not decrease its lexicographical order. So hence we'll say that we'll try to pick a element that is the smallest in the string and is available at the last. So this is what we needed to do in problem B. Here's the code for this. So we'll firstly take the value m. So initially we are saying that let's assume that the 0th element is the smallest element, and then we'll start traversing the string. At any time, if you find an element that is smaller or equal to the current element you are having, then you'll say let's use that one. So you'll update your lock, and what you'll do now is that now you'll be having the smallest element in the character m. So print that, because we want this to be at the starting, right? After that, print all the elements from 0 to lock, because you don't want to print the element at the lock itself or at the location itself, because that is something you have already removed, right? So don't print that. You can actually over here itself, you can remove this, but anyway, both of the things work. And then you print all the elements from lock plus 1 to n. Cool. So pretty straightforward question. Now coming to that question that made me study geometry within within the contest itself. So the problem is place for selfie. So the problem states a lot of gibberish. I'll not be going through that. So the basic problem is that you are given a parabola with the equation y is equal to ax square plus bx plus c, and a straight line with the equation y is equal to kx. Right. For example, these are the parabolas and these are the lines. So there can be n lines and m parabolas. What you need to satisfy is that for every parabola, you need to tell that if there's a line that does not even touches it or does not intersects it, right? If that's the case, in that case, print the k of the line or print the slope of the line, right? If it does not exist, then just print -1. So over here, okay, yeah. Over here, we have to print a yes if the line exists, and then the k for that particular line, or we can just print a no if no such lines exist. Now this is a problem completely based on geometry. I'll say less to do with computer science, but more to do with geometry, or everything to do with geometry. So the thing is that you can write the parabola as y is equal to ax square plus bx plus c, right? Now what you can do is you can say that your line is also y is equal to mx. Let's equate these. Okay, yeah, not yx but kx, because the variable they had given is k, so let's call it that only. So by equating, you'll get kx is equal to ax square plus bx plus c. You can rewrite this as ax square plus b minus k into x plus c is equal to 0. Now for this equation, if we want that the line and the parabola don't intersect, so for that to hold, the discriminant should be less than 0. Now the discriminant can be taken as b square, or the value of discriminant is b square minus 4ac, right? So b square minus 4ac needs to be less than 0. Now what is b over here? B is this entire term. So let's equate that. So we get b minus k squared minus 4ac is less than 0, right? Or we can say b minus k squared is less than 4ac. Cool. We have a square on this side, right? So we have a square. So let's open that. So b minus k is less than root of 4ac, right? But since we are opening it and it's a square, so it would happen on both the sides. So let's write like this. Now if we solve it, so we get 2 root AC is less than B minus K is less than root of 2 root AC, right? Now solving this further, we get K is less than B minus 2 root AC and K is less than B plus 2 root AC, right? This is the thing we wanted to check. Now, how would we do this in the code itself? So firstly, what we can do is like, okay, let me just write the pseudocode. Store all the lines or all the values of K, right? So this will be for all the lines. Then we'll say that we'll start traversing the parabola itself. Now for all the parabolas, we have three components or three parameters that define it. That is A, B, and C. Now in this particular A, B, and C, you can say that if this condition holds, right? If this condition holds, so how would you check that? Now let's say for all of these K's, I've already stored them in a set. Now why I'm taking a set? Just because it's ordered. So if I want to check that what is the element that is greater than this or lesser than this, that's the order of log n operation, right? So I've stored it in a set. Now I'll check if there's a value in the set which is greater than B plus root of AC. This I can calculate from here itself, right? B plus 2 root AC. If there's a value greater than that, and then I'll check. So if I have a value that is greater than this, and it should, greater than this, and it should be less than B plus 2 root AC. If such a value exists, then I'll print the X, right? Or I'll print the K, whatever you are calling it, right? If such a value does not exist, then I'll print a -1. So this was the logic for this equation. I know you would feel that most of it, this is just mathematics and not general DSA what we study, but I can't change the context and it is what it is, right? So let me move you to the solution for C. Okay, so yeah, this is the solution. Firstly, I'm taking all the K's, right? I'm inserting them. After that, I take the values A, B, and C, and then I have to check that my K square, okay, this is wrong. Okay, then I have to check that the value of K needs to be greater than B minus 2 root AC. That I'm checking over here. Now I'll check that if this value exists already, so it should not be end, right? And this particular value that I already got, this should be smaller than this value. If this happens, in that case I can print the value I got. If this does not happen, then I can print no directly. Cool. Any doubts in this? Aniket will definitely do the debugging, but that happens post the session. So once we have done with the recording, we'll go through the codes. Okay, cool. Let's move to the next problem. The next problem is, I'll say it's a good problem. For the first time, I actually saw usage of DSU and this tree problems in a single scenario. I initially was getting a wrong test case. That was just because of initialization. I was initializing it wrong. Anyway, so the problem states that you are given a tree with n vertices. Now consider fixed integer k. Then the graph gk. So we have an integer. If we are given a integer k, we can construct a graph gk such that it is an undirected graph with n vertices, where an edge between u and v exists if and only if the distance between these vertices u and v in the given tree is at least k. So the distance between the vertices v and u in this particular tree that they had originally given us, if it's at least k, it can be greater than k, it can be equal to k, anything, but it should not be less than k. If this condition holds, only then there would be edge between u and v, right? So then they have said that for each of these integers from k, for k from 1 to n, you have to print the number of connected components in the graph gk. So yeah, a lot of concepts are used over here. They've just mentioned the simple tag of trees because yeah, it uses DP on trees and it uses DSU. So both of them are actually covered in trees itself. The format of the input is fairly simple. So they'll be providing us with values u and v. That would be the edge. So basically edge is present between 1 and 2, between 1 and 3, between 2 and 4, 2 and 5 and 3 and 6. Cool. So now let's come to the point. How would we do it? And what's the basic intuition for that? Now, a lot of components in this question are standard problems. Now there's a CSCS problem. That is, let me see. This one. Yeah. Tree distance is 1, right? Now I already solved it earlier. So the benefit of solving standard problems is that you already have the code. Now this entire code actually remains as it is, right? So I saved time by copying this code, right? So this is a standard code which you can use for this problem. Now what we can do over here is, let's firstly define that when would two edges be connected, or when would two nodes U and V be connected. Now let's say this is a graph, or this is the tree we had, right? Now for each node, if I know that what is the other node that is most away from it. So let's call this node A. Let's call this B, C, D, okay, D, E, F. So I can say that from A, the node that is the closest to it, or sorry, the node that is the maximum farthest to it. So how long is the distance? So that distance is 1, 2. So 1, 2, 3, 4, right? So for A is 4, for B would be 3, right? For E it would be 1, 2, 3, right? For C it would be 2, no matter if you go this side or this side, right? It would be 2 only. For F it would be 3 again. For D it would be 3. So D can say that, okay, I'm gonna go to this, then this, then this. So the distance is 3. For E the distance is gonna be 4, and for F the distance is gonna be 3 again, right? So these are the values they can already calculate. So how like what is the farthest neighbor I have? Now why I'm even interested in this value? Because the problem states that in the graph we are gonna build, right? The edge between two vertices would only occur if they are that distance apart. So by that knowledge, what I can say is that if I already have a graph constructed, from that particular graph, removing the things is definitely a bit difficult, right? So if I, let's say, if I go from I is equal to 1 to n, or k is equal to 1 to n, so that would basically mean that two edges would be connected if and only if their distance is at least 1, right? So two nodes would be connected if and only if their distance is at least 1, or the distance between the two nodes is at least 1. Now every node has a distance at least 1 with the other. So basically you will have the entire graph, right? Then I'll say, okay, now k is equal to 2. So from this graph now I'll have to remove the nodes, right? Or I have to cut the edges down. Now this becomes a hectic task. But what I can actually do is, so here it was n not k, yeah. But rather what I can do is I can walk in the alternate fashion, or in the opposite fashion. So I can say I'll start from k is equal to n, right? I'll go to k is equal to 1. Now why so? So initially I know that k is equal to n, and in a tree I cannot have the distance between two nodes equal to the size of the node, because even in the worst case where you are having a flat tree like this, right? Even in this kind of a scenario, the distance is gonna be n minus 1. The maximum distance is gonna be n minus 1, right? So initially all of these nodes would be individual components, right? So all of these nodes are individual components. The number of components in this graph is n itself. Now what would happen is that when my k is equal to n minus 1, I would simply check that how many nodes were there in this initial tree that were having a value, or that were having the maximum distance from this node to another node equal to k, right? Greater than or equal to k. Now, no matter how many nodes are there, they would automatically become connected. Now you might ask how. So let's say over here I say that all the nodes which are having value 4 should be connected. So A would say that greater than or equal to 4 should be connected. So A would say that cool enough, I can now connect all the vertices that are distance 4 from me. So the distance at 4 from A is actually 4, E4 itself, right? So this would get connected. Okay, so now we'll be having the graph like A and E would be connected. All the other nodes won't be connected. Now we'll check for k is equal to 2 or k is equal to 3. Now over here, the nodes which are still present, so we have not already processed them. We have already processed A and E. The nodes that still remain in this graph are B, C, D, E and F. Now all of these nodes are connected. How so? Because the nodes we initially processed, right? The nodes we initially processed, they definitely would be having some sort of a connection with node B, because when it was saying that my farthest node has a value 3, it definitely needs to be one of these nodes itself, right? So B would be connected to this. In this case, B is connected to E, right? So as soon as B gets connected to E, now E would say, let's see to which I'm connected. So E is also connected to one of those nodes. So E is connected basically to both of these, right? So E is connected to A and to E, both via distance 4 itself. So he'll say, okay, I'm also connected to this. So E would also get connected. Similarly, F would say the same. So they'll start forming a structure, right? And this is what you need to do in that. So you'll say that, okay, now this structure is getting formed. So as soon as some node, okay, so when some node gets released from this structure itself, then the number of components decrease, right? Because if you are, let's say you are having some free nodes, and you are having this kind of a structure right now. So this is a component, this is a component, this is a component, this is a component. But as soon as this node attaches to this, so the number of components decreases by 1. Components decreases by 1. Okay. Meanwhile, when I was explaining you the solution, I figured out. So just while explaining the solution right now, I came to the conclusion that what I had done was actually not even required. We can actually make it even simpler. Just give me a second. Okay, so this is what I did. Instead of doing this, I can simply say components minus minus. That would work exactly same. Okay, let's just see if it works. Fail. Okay, it fails. But why? Give me a second. Let me try to. Okay. Should I push back? This is fine. Okay, initially it starts setting the values. Oh, got it. Yeah, makes sense. Okay, just make a check over here. This node is not equal to. Wait a second. If it doesn't work, anyway, I'll try to come over here again and check it. Yeah, it works actually. This is the valid solution. So you didn't even need union find over here. So all of this code can actually be removed. And because of this code itself, I got error. So if this is removed, don't worry, I'll explain you the logic. Just give me a second. Just making it easier for you to understand. Okay, we can remove this as well. Yep, makes sense. Okay, cool. So what we are doing in this logic. So firstly, we'll need to make this particular array wherein we need to make this DP array, which tells me that from a node, how distant is the other node, right? Or from every node, what is the longest distance in the tree available, right? So in order to make that, we have a standard algorithm. Now, if I start explaining that, this video is gonna get very, very long. But we already had a session on DP on trees, right? If you have watched this session, this question shouldn't be that tough to you. I would highly recommend to you to do this question, because this is a straightforward question and definitely would build a lot of concepts that would be required later on. So you can do this question. But what this question does in like how we calculate this is that we start a DFS traversal, right? We pick any node for that matter. It doesn't matter what is the node you are picking, right? So, okay, let me just give you a brief insight over here as well, so that you are not lost per se. So let's say this is the tree we are having, right? In this tree, we'll pick any node or any root. Let's say I'll pick this as the root, right? Now I'll start going down, and then each node would return me something. Now what would this return? So every node would return me the node value, that is 1 plus whatever value it received from its children, or whatever maximum value it received from its children. So basically, while doing this, we would be able to analyze that, okay, how many nodes, or what is the maximum distance to your nodes, right? Maximum distance from this node to the node below you, or what is the maximum distance in your subtree, that you'll know, right? And you'll store this particular value, but not just this particular value, you'll actually store two values. So you'll store the maximum one and the value that was smaller than your maximum or less than or equal to a maximum. So let's say you are having this kind of a structure, right? So over here you say that, okay, this subtree actually has two edges. So you'll say over here that your DP contains two values. So that would be 2 from here. So DP of root would contain 2 from here. And over here also there are two edges, right? So 2 from here. In case this edge was not present, then you would have stored 2 and 1, right? After that, we again start the DFS traversal from the same node, but this time the function is a bit different. What this function does is, since this function already knows, so the DFS2 or the another DFS call, this function already knows what is the maximum value in its subtree, right? And when we'll be processing it, so we'll already say, so let's say this is the value root, this is the root, right? And from the root, let's say you go to a child. Now, what would be the node that would be the most away from this child? So you have from this child or from this node, you have several options. Either the path could have been somewhat like this, right? So this is also path, right? So your path could have been something like this, or your path is something like this, right? The longest path is in your subtree or it's not in the subtree. Basically, that's the two possibilities you can have, right? So whenever I'll be going from the root to my children, I'll just check. So initially we already saved two values, right? That were mx1 and mx2. Corresponding to that, actually also had saved the vertices corresponding to which we were having the values mx1. So we'll say that, okay, corresponding to your child ch1 you are having mx1, and corresponding to child, let's say chy, you are having mx2. Now we'll check if the child at which now I'm going in the DFS traversal, it's chy. So to this particular child, I'll not pass mx1, but I'll pass mx2 to this child. But if it's any other node, then I'll pass mx1 to that, right? So once you're done with this, so currently coming at this node, you'll already have information as to what are the longest nodes in your subtree. But now you'll also be having information about about which is what's the longest path. If you start traversing your parent, that would already be have fed by your parent in mx1 or mx2, right? Or whatever like function or parameters were there. So in our case, okay. So yeah, I'd also passed the value parent size. If you want, I'll give you the submission link. You can go through this particular solution. But this particular code right over here, it's pretty standard. It's a standard problem. That's why I'm not discussing it in detail. Cool. After you're done with that, so then comes the easy part. So firstly, you take the array, right? And then all of these things are already been done by that code. So the rest is the array, which actually contains distance of the longest edges or longest path from node I. So this thing we already know, right? Now what we do is, since we want to have the biggest the nodes with the biggest distances first, right? But we also need to know their indices, because that's what would be required, right? So what we're doing over here is, actually when because I was using DSU first, that's why I stored the indices. You can even get rid of that and still the answer would be valid. But anyway, let me just walk you through this code itself. Then you'll sort it. Sorting is required because we want the biggest distances to be at the end, or you can take it at the to the first, whatever you want. The number of components initially would be n, because all the components would be single nodes which won't be connected, right? And then you can say I'll be going from k is equal to n till the time it's greater than or equal to 1 and minus minus. So what's I now? I is sz minus 1. Now what's sc? Sc is basically n. So because we are using zero base indexing, so our vector v would contain n elements, right? Since I have sorted them from in a non-decreasing order, so I want to be at the last element first, because that would be the biggest element. So I'm gonna go from right to left. I'm gonna check if this particular value is greater than or equal to k. If it is so, then I can remove it, right? So I'll remove it. Else, if it's not greater than or equal to k, then I'll break it. And whatever happens. So if I'm removing it, so technically one thing more is happening. As soon as I'm removing it, the number of components are actually decreasing, right? If the number of components are decreasing, I also need to report that. And either way, if it decreases or not, at every iteration, you want to know how many number of components are there. So you'll be pushing that to your solution, right? After that, you have to reverse this, because they wanted to have the count from 1 to n, but you are giving them the count from n to 1. So you need to reverse it also and then just print the solution. So yeah, that's it for this problem. I think this was a nice problem. Maybe a standard one, but yeah, still a nice problem. Okay, I think, okay, no worries. Yeah, cool guys. So any doubts in the explanation? We'll be going through the codes now. I'll stop the recording, but any doubts in the explanations? Cool, let me stop the recording then.